In the present session, we are going to discuss a low frequency response of BJT amplifier. Objectives of this class is effect of a capacitor CS, effect of coupling capacitor CC, effect of coupling capacitor bypass capacitor CE on the frequency response of the RC coupled BJT amplifier. If time permits, we have to discuss one numerical at the end of the class. That amplifier circuit as shown in figure. If you observe that circuit diagram, which consisting of the three capacitors CS, CC and CE, and then because of this a frequency dependent components, the amplifier response, that gain of the amplifier varies at low frequencies. Now we have to consider one by one. While discussing the coupling capacitor CS, we will ignore the effect of the other capacitors, and then we have to define the what is the cutoff frequency and then what is the gain of the amplifier when the input is applied. Let us consider that a RC coupled amplifier, this circuit consisting of a resistance RS, voltage Vs is applied, and then the bypass capacitor CS, R1, R2 is applied to the resistance RE, and this capacitor CE is grounded, and then resistance RC is connecting to the power supply VCC. This load resistance is connected through a coupling capacitor CC, and then load RL is connected to the output, and then output is to be taken across RL. The value of this is C. The objective of this class is we have to determine that effect of these three CS, CE and CC on the gain of the amplifier. First, let us consider the effect of coupling capacitor CS. If we consider the effect of the coupling capacitor, we need to determine what is the resistance at this point Ri. Because we have to determine means we have to replace this entire circuit with its equivalent resistance. Means to determine the effect of the coupling capacitor, we are ignoring the effect of that CE and CC here. Then this circuit becomes this RS is in series with CS, and then this is to be applied to the amplifier. The input is connecting between this. Then the voltage across this is denoted with Vi. Means even if you apply an input voltage via source voltage, the voltage appears across the base emitter terminal, or this point is Vi. This is given by this expression. Then what is there within this resistance amplifier? This amplifier, when you are looking into this amplifier, that output means that input resistance Ri is to be present. This resistance is existing. Then this input voltage Vi is voltage drop across the Ri. This circuit is redrawn as the RS, CS and Ri. Then the voltage across this is Vi, and then this is Vi. Now we define the ratio of that. Means first, instead of determining the overall gain of the amplifier, we need to determine what is the effect of this due to this capacitor CS, what is the effect on that input. If this ratio Vi by Vs, that will give the also effect on the overall gain of the amplifier. For this case, we need to determine Vi. For determining on Vi, this CS is to be replaced with a reactance minus JXCS. Minus JXCS. Then what is an input voltage? Input voltage Vs and output voltage to be across this. Therefore, you are applying KVL, the current flowing through this is I. Then that Vi is equal to I into Ri. Okay. We need to find I. To find an I, you have to apply KVL to the circuit shown in that figure. Then this is equal to Vs minus I into Rs minus I into minus JXCS minus I into Ri equal to 0, where that XCS is given by, it is the reactance of a capacitor, then this is given by 1 by 2 pi f into Cs. You have to solve this equation for the current, then that current is equal to I into Rs plus Ri minus JXCS equal to Vs. Therefore, I is equal to Vs divided by Rs plus Ri minus JXCS. Substitute this equation 3 into 1, then you will get a Vi equal to Vs into Ri divided by Rs plus Ri minus JXCS. The Vi by Vs, that ratio is given by Ri by Rs plus Ri minus JXCS. If you observe the equation 4, this is a complex in nature, then this is means it is in the coordinate form. Therefore, because of this complex in nature, both that Vi by Vs varies, that gain of the amplifier is also varies, and the phase of the amplifier is also varies as a function of frequency. Now, we need to determine what is the magnitude and the phase. For this, substitute to, first you have to substitute equation 2 into 1, and then you have to calculate Vi by Vs is equal to Ri divided by Ri plus Rs minus J divided by 2 pi FCS. Normalizing this, then you are going to get this is equal to Ri divided by, if you take Ri plus Rs common in the denominator, you are going to get 1 minus J divided by 2 pi FCS into Rs plus Ri. Okay. For this, we need to calculate a magnitude and a phase. If you observe, this component Ri by Ri plus Rs is independent of the frequency, hence this ratio is to be remains constant, then we can say that A is to be defined as something called AV mid. For this circuit, then this is equal to 1 minus J 2 pi, 1 minus J divided by 2 pi FCS into Rs plus Ri, where A mid is given by, this is equal to Ri divided by Ri plus Rs. Now, you have to find, because this is a complex in nature, you have to determine a gain of this. Hence, we have to convert into the magnitude and a phase. We know that already, if of the form, means if that a number is of the form A plus or minus JB complex, then its magnitude is given by a square root of A square plus B square, and that phase of this network is given by, or as a number is given by a tan inverse of B by A. Using this relation, we need to find that a magnitude and a phase of a network. Then you are going to get Vi by Vs magnitude from the equation 5. It is given by A mid divided by 1 minus, because that is square root 1 plus divided by 1 divided by 2 pi FCS into Rs plus Ri whole square, and phase equal to, because you have to considering the a phase of the numerator and the phase of the denominator. For the phase of the numerator is 0 and phase of the denominator is a tan inverse of 1 divided by 2 pi FCS into Rs plus Ri. Okay. Where this is, there is a negative sign is there, therefore it is minus tan inverse. We know that already from the trigonometric identities, a tan theta, tan of minus theta is equal to minus tan theta, then this will becomes a tan inverse of a 1 divided by 2 pi f Cs Rs plus Ri. We got a magnitude and a phase. If you are observing both a magnitude and a phase, that both are as a function of frequency f, therefore, as the frequency varies, that both gain as well as the phase varies. Now, let us consider only the magnitude of this network, then we have to consider under what condition this network transfers the maximum power. What is the condition for that? Normally, we are used according to the maximum power transfer theorem, a input impedance equal to a source impedance or the resistance. Therefore, according to this is equal to Ri is equal to a complex conjugate of this, means that is Rs plus minus j x Cs. Otherwise, if you are considering in the magnitude, we are going to get this is equal to that complex conjugate. Therefore, you can say that x Cs is equal to Ri plus Rs. Or we have to take the complex conjugate of this number, or if the reactance of this capacitor is equal to the resistances of these two Rs and Ri, then this network transfers the maximum power. Therefore, we need to calculate what is the condition for that. This reactance is variable or it depends on frequency. As the frequency varies, frequency of the input signal varies, correspondingly this reactance is also varies. Hence, that all frequencies, that reactance of the capacitor is not equal to Ri plus Rs. This is the reactance of the capacitor is equal to Ri plus Rs only at a specific frequency. That frequency is to be defined as we can say that at f is equal to FLS. At the frequency f is equal to FLS, that reactance of the capacitor equal to Ri plus Rs. Then from the equation 2 we can say that Xs is nothing but 1 pi 2 pi FLS into Cs, this is equal to Ri plus Rs. Hence, this circuit is becomes FLS is becomes 1 divided by 2 pi Cs into Rs plus Ri. Now, what is this FLS? What is the value? Because we are defining some frequency, f is equal to FLS is a one frequency. What is this? You have to define this frequency. How do you define? You have to substitute this a 1 by 2 pi Cs into Rs into Ri into the equation 9 into this 7, that is again then a magnitude of the amplifier is given by Vi by Vs is given by A mid divided by square root of 1 plus a reciprocal of this is nothing but an FLS. Therefore, you can write FLS by F whole square. This is the gain of the amplifier. Now, you have to plot a frequency versus gain or Vi by Vs. This is known as a Bode's plot. For the Vi by Vs, that response is given by, means if you plot a frequency versus a magnitude Vi by Vs, it is a ratio. If you consider the ratio of this, when that frequency f0 means at DC conditions, then what is the reactance of a capacitor? When this means at DC means f is equal to 0, then that Xcs reactance of a capacitor is equal to 1 by 0, that is equal to infinity. Hence, this circuit is to be behaves like a open circuit. Because of that reason, there is no current is to be flowing through the circuit. Hence, that input voltage is also 0, output voltage is also 0. Hence, that gain of the amplifier is becomes 0, Vi by Vs magnitude. As the frequency varies, that reactance of means if the frequency increases, that Xcs decreases. How this varies? Because if you observe this denominator, if that because this value FLS by Fs, FLS is to be constant, because this is given by FLS is given by 1 by 2 pi Cs into Rs plus Ri. where CS, RS and RI are the circuit elements of a network. If these elements are constant, then that frequency is also constant. Only variable is frequency f. For this case, as the frequency increases, reactance is decreases. Means as the reactance decreases, means if you consider magnitude, this frequency is increases, this ratio is decreases, and then the gain of the amplifier goes on increasing. How it is varies? It is increasing exponentially, because this is a nonlinear device. A square root of that 1 plus x square, because of that reason this frequency response of this amplifier is goes on increases, and then it reaches some constant value. This frequency value is nothing but A mid. Okay, this is the frequency response at when f is approaches to the infinity. F approaches to the infinity, this circuit element means that CS is acting as a, because that reactance XCS is approaches to the 0, then it is acting as a short circuit. Therefore, your output voltage are Vi by Vs is equal to A mid, that is already defined, that is nothing but Ri divided by Ri plus Rs. Hence, this value is to be equal to this. Now, what is this value? Frequency on this frequency response. Now, if that a frequency f is equal to FLS, Vi by Vs magnitude, this is equal to A mid divided by square root of 1 plus 1, this is equal to A mid divided by root 2. Then this is nothing but at f is equal to FLS, the gain of the amplifier equal to a square reduced by the factor or equal to the a mid band gain divided by root 2. Means we have to plot here, if this value at f is equal to FLS, this value equal to A mid by root 2. This gain is nothing but a half power gain, because when this condition is XCS is equal to RS plus RI, then the gain of the amplifier is nothing but networks transfers the maximum power. Its transfers on the maximum power is half of the input power. Hence, this frequency is known as a half power frequency, cutoff frequency. If you take a decibels gain in Vi by Vs in dB, this is equal to 20 log A mid minus 20 log root 2. This value equal to a minus 3.01 decibels. That half power cutoff frequency is also equal to the a minus 301 dB. Hence, we named this FLS is named as a upper cutoff minus 3 dB cutoff frequency due to a coupling capacitor CS. Okay. Therefore, hence we can define this is to be named as a upper cutoff frequency of the low frequency response of an RC coupled amplifier. This frequency is known as a minus 3 dB cutoff frequency. Next is we have to consider the what is the effect of this coupling capacitor CC. That coupling capacitor CC means you have to looking back into the a network or the amplifier, means you are looking back into this point, that is denominated as R0. What is R0? Means this complete circuit is to be defined as or replaced with its equivalent value. Means you are going to get this amplifier is the network box, then this is connecting through that CC and output is to be taken across RL. This is V0. You have to consider effect of a coupling capacitor CC at the load. For this case, what is the effect on this? When you are looking back into this resistance is R0. This you have to considering something called R0. That R0 is nothing but an output impedance of a network when Vs is equal to 0. Then this amplifier circuit is to be replaced with, from the small signal analysis models, transistor model analysis, we can R naught is to be defined as something like this. R naught is the internal resistance of a transistor is parallel with a capacitor coupling, a collector resistance RC is in series with this capacitor CC, and then output is to be taken across RL. This is V naught. This is the equivalent circuit when Vs is equal to 0. Okay. Means we have to replace this transistor with this circuit, means this equivalent circuit is driven by what? Next question. We know that already. If you replace this transistor with a small model, small signal model, this is looks like something called a beta times Re is connecting like this amplifier, and then this is you are going to get. This is nothing but beta times Ib. Means when Vs is exists, if that Vs is not equal to 0, then this circuit is driven by a constant current source, that value is equal to beta times Ib. Then when Vs is not equal to 0, then the circuit is to be replaced with a constant current source is in parallel with, I can replace this already we defined the parallel combination of R naught and RC is nothing but R naught. This can be replaced with an R naught and then a capacitor CC, and we have to take an RL. This is your V naught, this is CC, where R naught is defined as R naught is in parallel with RC. Okay. This is beta times Ib. Now we have to determine that ratio, what is the output voltage when Vs is, where this a current Ib is proportional to the input voltage Vs. To determine the proportional to this means we have to find an Ib, means that is a proportional to Vs. Therefore, instead of the constant current source, but we want the ratio of V naught by some input voltage. Using a voltage transformation or source transformation technique, we can say that the voltage something called V dash, where V dash is nothing but a product of this constant current, and I can say simply and constant current I into R naught. V dash is equal to something called I into R naught. Then this is in series with R naught, that R naught is given in an expression 1. Then this capacitor CC, and then output is to be taken across load resistance RL. This voltage is V naught. Now we need to find that gain at the output stage due to the coupling capacitor CC is taking the ratio of V naught by V dash, where V naught is equal to V dash is equal to I into R naught. The direction is negative side, therefore you are going to get a gain of the amplifier is negative. At this moment you have to ignoring the negative sign, therefore you have to take only a positive value. Now we need to determine the output voltage and then gain due to that input voltage V dash. For this, that V naught is equal to, from this equation, the current flowing through called something I1, then this is equal to I1 into RL, where I1 is to be determined by applying KVL to the circuit, then you are going to get V dash minus I1 into R naught minus I1 into minus JX CC minus I1 into RL equal to 0, where that XCC reactance of a coupling capacitor is given by 1 by 2 pi f CC. Solve this equation for the I1, then this equation expression is becomes I1 into R naught plus RL minus JX CC equal to V dash. Substituting this equation into the equation number 2, then V naught is equal to V dash into RL divided by R naught plus RL, and also substitute equation 3 into this, you are going to get minus j divided by 2 pi f c c. If you take normalizing the denominator, then you are going to get V naught by V dash equal to RL divided by R naught plus RL. If you take common, then this will becomes 1 minus j divided by 2 pi f c c into R naught plus RL. Now, if you are observing this equation 4, this is given by RL by R naught plus RL is equal to, this is a complex in nature. Once again, we have to consider this is the something called a mid gain, that is due to the coupling capacitor CC at the output stage. This ratio remains constant. Therefore, we can say that a V naught by V dash is to be a constant, is called something called K divided by 1 minus, or simply we can also call AV mid. AV mid, this is equal to 1 minus j divided by 2 pi f c c into R naught plus RL. It is in a complex in nature. Once again, similar to that, this then you have to converting into this. For this circuit also, this network transfers the maximum power if and only if from this circuit this R naught plus RL equal to a reactance of a capacitor. Therefore, we can say that if XCC is equal to R naught plus RL, if this condition is satisfied, then this network transfers a maximum power through that network. Once again, this XCC is a depends on frequency. At all frequencies, that a reactance of a capacitor is not equal to the resistance and the sum of the resistances. Means we can say that at X F is equal to FLC, that FLC is due to the a tuning frequency or a cutoff frequency, but due to the coupling capacitor CC, then this XCC is equal to 1 by 2 pi FLC into CC equal to R naught plus RL. Then you can get that FLC is equal to 1 divided by 2 pi CC into R naught plus RL. Then the frequency V naught by V dash is given by AV mid, where AV mid is given by this RL divided by R naught plus RL divided by 1 minus J FLC by F, where AV mid is equal to RL divided by R naught plus RL for this circuit. Now, what is the frequency? Because this is a complex in nature, you have to convert this one into the polar coordinates form. Then your V naught by V dash is magnitude is given by AV mid divided by square root of 1 plus FLC by F whole square. Then phase equal to tan inverse of FLC by F. This is equation. Now, what is this frequency response of this V naught by V dash also? This V naught by V dash response is identical to that response of that is due to the CC. If you are observing that, if you plot a V frequency versus a magnitude V naught by V dash, if the F is equal to 0 under the DC condition, the reactance of the capacitor is acting as a open circuit in this. reactance is means of a capacitor becomes infinity, this capacitor is acting as a open circuit. Thence that a voltage gain at this point, a DC condition, is 0. As the frequency increases, this gain of the amplifier varies exponentially, because that is 1 plus FLC by F whole square, it is a square of that function, then this response is to be like this. As the frequency approaches towards the infinity, that gain of the amplifier remains constant, that gain is nothing but AV mid. Then from the equation 6 we defined some frequency FLC. What is this? How do you name it? That naming is to be done if you at F is equal to FLC, then that ratio V naught by V dash equal to AV mid by square root of 1 plus 1, this is equal to AV mid by root 2. If you are considering this is the frequency, at this frequency F is equal to FLC, this is AV mid by root 2. This FLC is also known as a upper minus 3 dB cutoff frequency due to the coupling capacitor CC. Therefore, this is also known as a cutoff minus 3 dB cutoff frequency due to the coupling capacitor value. Next is we are separately calculate the either CS and CC. Then what is the effect of that CE on this amplifier? When you are considering CE, you are ignoring the other two capacitor values. This can be obtained. To analyzing this circuit, you are looking into this terminal. Instead of a CEC combination, you have to looking into the emitter and a ground. This resistance is to be denoted with RE. And then also neglecting this the capacitance value CC and CS. For this, you are using a small signal model, then this can be defined when to find effect of, first we are right heading effect of CE. First step is you need to calculate the equivalent resistance of an RE like RI and R naught. When you are finding an RE, you set Vs is equal to 0. This RE is nothing but that voltage drop between the emitter and a ground. We can say that simply VE, and a current flowing through this point emitter is it is denoted with IE. Means we need to find the ratio of VE by IE with setting that Vs is equal to 0. For this condition, you have to replace a transistor with a small signal model, then we can able to get RE value. For this one, you have to write this is beta times RE, this is a transistor is replaced with this a capacitor, this is beta times IB. Okay, there is a resistance R naught and so on. Because when you are considering that R naught finding that this RC and RL is also, without neglecting this, not neglecting, it is a open circuited load resistance. So, therefore, RC and RL is becomes infinity. Then from this point you are connected this RE. You are looking into this point is RE. From this base, this R1, because you have to set that VCC is equal to 0, R2 is in parallel with R1, and then that Vs is equal to 0, this acting as short circuit, then this Rs is also connected in parallel. When this Vs is equal to 0, that constant current source of this amplifier, a constant current source IB is also 0, this constant current source is acting as a open circuit. Then that equivalent circuit of a amplifier to determine RE is shown in this figure. For this we need to calculate. When looking into this resistance R1, R2, Rs, these three resistances are connected in parallel. Therefore, we can replace this is an Rs dash is in series with this beta times Re, then you are looking into this is Re, this point is grounded, you are looking into this point. Now, what is the current flowing? The next question is, can you guess what is the current flowing through this beta times Re and what is the current flowing through this Re? From this, if you are observing this circuit, these two are connected in series. means the same current is to be flowing through the circuit. For the same current is to be flowing through the circuit means from the transistor analysis, that current flowing through this from base to emitter is IB and current flowing through between emitter to ground is IE. These two currents are different, but if you redrawn this equivalent circuit, these two resistances are in series. When these two resistances are series means that current flowing through the circuit is also remains same. But by definition, that RE is given by VE by IE with that Vs is equal to 0. Means you have to convert this base current IB into the emitter current IE. We know that emitter current IE is equal to 1 plus beta times IE. This is approximately equal to beta times IE. The one expression. And also where RS dash is from this circuit, we defined that is equal to RS is in parallel with R1 is in parallel with R2. Okay. Now, when this is replaced with IB, from the equation 1, you have to replace IB is equal to beta times, IB is equal to IE divided by beta. Means you have to write this is in terms of current IE. Hence, this circuit means this IB is equal to IE by beta. You have embedded this beta value because I want current flowing through that network should be IE, means you have embedded this beta value into the resistance, then that network becomes RS dash by beta, hence that current flowing through this becomes IE, and this resistance becomes RE, then this resistance is RE only. Here you are looking into this path. This is short circuited. Now, when this resistances are divided by beta, then that current flowing through the entire circuit is equal to IE. When you are looking into this network, then RE is nothing but these two resistances are connected in series and is in parallel with RE. Hence, this expression RE is equal to RE is in parallel with RS dash by beta plus RE. Okay. You are found that this resistance RE means when you are looking into the network, this network resistance, transistor network resistance value is equal to RE. Then this circuit, as transistor amplifier circuit behaves like or looks like, this is a transistor, there is some resistance RC equivalent VCC, then at the emitter this is a parallel combination of R into small re, it is not equal to this RE, this is equal to, when you replace that entire circuit with an RE and this resistance is CE, then this is grounded. Output is to be taken across this point. If you are applying that Vs is applied here, then Vs is to be applied, then that frequency varies, then that reactance of this a parallel combination is varies, then the gain of the amplifier is also varies. Here I am not interested in that gain versus frequency, gain, that voltage gain, that voltage gain at mid frequency remains constant. We are interested in what is the gain of the amplifier at low frequency. For the low frequency equivalent circuits, we need to find what is the cutoff frequency of this network. We know that once again, you have to use that maximum power transfer theorem, that reactance of this RE equal to CE is equal to RE. Under that condition, this network is transfers the maximum power. Then you are writing this RE is equal to X C. Then where X C is equal to 1 divided by 2 pi F into C. This because Xc is depends on frequency f, hence the frequency response means as at all frequencies this reactance is not equal to Re. Hence, I have to define at f is equal to f L E, then this is equal to 1 by 2 pi f L E into C is equal to Re. From this you are going to get a f L E is the cutoff frequency, that is equal to 1 by 2 pi f L E into C. this is RE, small RE. This resistance is given by 1 divided by 2 pi CE into RE. This frequency is also known as a low upper cutoff frequency of the BJT amplifier. Okay. Now, we derived an expression for a cutoff frequency due to the CS, cutoff frequency due to the CC and cutoff frequency due to the CE. If you summarize these expressions and then a frequency response, we need to that first is FLCS, that is due to the this frequency that is given by 2 pi CS into RS plus RI, and then this is FLC that is due to this frequency, that is equal to 1 by 2 pi C into R naught plus RL, and FLE that due to the emitter bypass capacitance, this is equal to 1 by 2 pi CE into RE. This is the summary of this objective of this class, or a summary of this class. Now, my only one question for you people is, if capacitance value CS, CC and CE are equal and then these cutoff frequencies are equal, question is, if means FLS is equal to FLC, this also equal to FLE is the question mark. Either these two cutoff frequencies are equal. How do you justify this? If you say yes, you have to justify. If you know why it is not equal. If you think in this direction, then we can able to analyze these the frequency response of this amplifier due to the CS, CC and CE is completely understood. Because this, my answer is that FCS is not equal to FLC is not equal to FLE. Okay. Next, once again you have to why. Why did these two are not equal? Reason is, if this, when you are looking into the input side, we know that emitter base junction means base emitter junction is forward biased. Because of this forward biased, the resistance Ri is lower. One reason. Second one is a base collector junction or a collector base junction. This is reverse biased for a distortionless amplification. Hence, the R naught is higher. Even if this RS, CS, CC and CC and RL are equal, but due to the a biasing of this transistor junction, base emitter junction and a collector base junction, this Ri is not equal to R naught. Hence, this FCS is not equal to FLC. Similarly, this RE, because this depends on C and RE is depends on this input resistances RS, R1 and R2. Hence, that this is also not equal to FLE. Therefore, when you are defining a frequency response of an amplifier, that these three cutoff frequencies for a common same a capacitance values, you are going to get a different frequency response. If you plot the frequency response of the amplifier with in gain in decibels, if you plot, this is a frequency, this is V0 by Vs in dB. That frequency response is to be something like this. This is the frequency response, and then it is, this is FLE, sorry, FLS, and then if you consider this is to be somewhere FLS, FLC, if you consider, you are going to get some frequency that is to be FLE. All these are varies means increasing at the rate of a 10 dB per decade, 20 dB per decade, because that is a 20 log. Therefore, if you are to considering this ratio 20 dB, this is to be a frequency response of the amplifier due to the various frequency component. Normally, if you are consider the lower cutoff frequency, means upper cutoff frequency of the low pass filter, low pass response of an amplifier, you have to consider that highest cutoff frequency of the transistor amplifier. You are chosen for, in this case, if this FLS is greater than less than FLC is less than FLE, hence you have to choose that FLE is the higher cutoff frequency of this transistor amplifier. Then you have to for a low frequency response, you have to consider this is the a lower 3 dB cutoff frequency for the RC coupled amplifier. This is the a summary of this class. In the next class, we are going to take one example on the RC coupled amplifier, and then later we will continue in the next session a low frequency response of an FET amplifier. Thank you.